While dinosaurs would later dominate memory as rulers of the land, the oceans of the Jurassic quietly became something far more unforgiving, because water allowed size, speed, and predation to scale without the limits imposed by gravity or terrain. These seas were not empty backdrops to terrestrial evolution, but densely occupied systems where survival depended on constant motion, rapid response, and the ability to exploit food chains that stretched vertically rather than horizontally. Unlike land ecosystems, where dominance could be localized to valleys or floodplains, marine power extended across basins because currents carried energy, nutrients, and predators far beyond any single shoreline. In this world, the largest animals on Earth were not plant-eaters lumbering between forests, but active hunters built for pursuit, interception, and endurance in an environment that never stopped moving. Ichthyosaurs emerged as some of the earliest masters of this system, shaped less like reptiles than like fish or dolphins. Because hydrodynamics punished inefficiencies more harshly than any land-based competition, their bodies became tools optimized for speed and stamina, with crescent tails, streamlined torsos, and eyes so large that vision itself became a weapon in dim, shifting underwater light. Plesiosaurs followed a different path, sacrificing raw speed for maneuverability, because long necks and broad flippers allowed ambush strategies that turned patience into lethal advantage. These two lineages did not simply coexist, but partitioned the ocean by depth, prey type, and hunting rhythm, reducing direct competition while increasing overall predation pressure on everything below them. Fish, ammonites, and squid-like cephalopods did not evolve in isolation, but under constant selection for escape, concealment, and rapid reproduction, because failure was immediate and unrecoverable. The Jurassic Ocean therefore became an arms race measured not in generations of peace, but in continuous pressure, where every adaptation provoked a counter-adaptation elsewhere in the food web. Oxygen levels in the Jurassic seas played a quiet but decisive role, because higher atmospheric oxygen translated into richer surface waters and deeper habitable zones for active swimmers. With more oxygen available, predators could sustain higher metabolic rates, allowing longer chases, faster growth, and greater body size without the constraints that limited terrestrial animals. This abundance did not create stability, but volatility, because dense energy flow amplified the consequences of disruption rather than buffering them. Storms, volcanic events, and shifts in sea level reverberated quickly through marine systems. Yet recovery followed just as rapidly, driven by reproduction rates far faster than those on land. Plankton blooms could collapse and return within seasons, rebuilding food chains from the bottom up long before forests or soils had time to regenerate. As a result, extinction events that devastated terrestrial ecosystems often appeared muted or temporary in the oceans, not because damage was less severe, but because marine systems were structurally prepared for death in the sea did not clear space permanently, but temporarily, because currents redistributed life as efficiently as they redistributed nutrients. This resilience allowed predators like Ichthyosaurs and Plesiosaurs to reoccupy niches quickly after disruptions, reinforcing dominance rather than resetting hierarchy. Over time, parallel patterns emerged between ocean predators and land dinosaurs, not through shared ancestry, but through shared selective pressures favoring size, speed, and sensory dominance. Teeth sharpened, jaws strengthened, and necks lengthened in different environments for the same reason. Prey that could move faster forced predators to do the same. Yet the ocean imposed additional demands because buoyancy removed weight limits, allowing predators to grow larger without sacrificing mobility. This freedom reshaped evolutionary ceilings, making the sea the first place on Earth where sustained gigantism became practical rather than exceptional. Unlike land predators, which were constrained by energy costs of locomotion, marine hunters could glide, coast, and ambush with minimal expenditure. This efficiency made the ocean a place where danger was not always visible, because movement could be silent, sudden, and multidirectional. Prey species responded by evolving shell armor, rapid life cycles, and collective behaviors, creating complexity that fed back into predator specialization. Over millions of years, the Jurassic Ocean hardened into a system where balance existed only in motion, never in rest. Stillness became vulnerability, because even pause invited interception from above, below, or behind. The water column itself turned into layered territory, with predators specializing not just by prey, but by depth, light, and temperature. This vertical partitioning intensified competition while reducing overlap, allowing multiple apex hunters to exist simultaneously without collapse. On land, dominance often erased rivals, but in the sea, dominance multiplied them. The result was not a single ruler of the ocean, but a hierarchy dense enough to leave no safe level unoccupied. For every large hunter, there existed smaller specialists, exploiting moments of weakness, injury, or exhaustion. Even the apex predators were never beyond risk, because the ocean did not respect size once movement slowed. Injury was therefore more consequential than on land, as blood and motionlessness broadcast vulnerability across long distances. Survival depended not just on strength, but on avoiding mistakes that could not be hidden. Over time, this relentless pressure shaped marine reptiles into creatures less forgiving of error than any land animal. The Jurassic Ocean became a place where evolution favored not dominance alone, but sustained performance under constant threat. In this world, power was not demonstrated in confrontation, but in endurance. Long before dinosaurs perfected rule over continents, the sea had already become a proving ground where failure meant disappearance. And once life learnt how to survive there, the land would never again be the most dangerous place on Earth. As marine reptiles entrenched themselves as dominant hunters, the Jurassic Oceans grew increasingly structured around energy transfer rather than territory. Because food moved vertically and laterally in ways land ecosystems never could. Primary production began not with plants rooted in soil, but with microscopic organisms suspended in light-filled surface waters, converting sunlight into chemical energy at scales that dwarfed terrestrial productivity. Phytoplankton blooms formed the invisible foundation of marine food chains, expanding and collapsing in response to temperature, nutrients, and circulation rather than seasons or geography. Zooplankton followed these blooms upward and downward through the water column, turning the ocean into a layered conveyor of calories that never fully shut down. Small fish and cephalopods fed into this system efficiently, because rapid reproduction allowed losses to be absorbed without long-term collapse. This created a paradoxical environment where death was constant, yet recovery was immediate, producing ecosystems that were both violent and resilient at the same time. Oxygen availability amplified this effect, because well-oxygenated waters allowed active predation to persist across wider depths and longer durations. Unlike stagnant or stratified seas of other periods, much of the Jurassic Ocean remained dynamically mixed, sustaining life far below the surface. This mixing reduced dead zones and expanded habitable space, increasing total biomass rather than concentrating it into fragile pockets. For large predators, this meant that food shortages were rarely absolute, but instead shifted spatially, forcing movement rather than extinction. Ichthyosaurs capitalized on this mobility, becoming wide-ranging hunters capable of tracking prey migrations across entire basins. Their endurance-oriented physiology allowed them to remain active over long distances, transforming the ocean from a patchwork of habitats into a continuous hunting ground. Plesiosaurs, in contrast, exploited structural complexity, using coastlines, shelves, and depth gradients to stage ambushes where prey density peaked. These differing strategies reduced direct competition while increasing overall predation efficiency across the system. As a result, no single prey population could dominate unchecked, because pressure arrived from multiple directions simultaneously. This distributed predation stabilized food webs, even as it intensified individual risk, producing oceans that were productive but unforgiving when environmental disruptions occurred, such as volcanic episodes or climate oscillations. Their impacts propagated quickly through plankton layers, rather than accumulating slowly in soils. Short-term collapses followed, but these were often followed just as quickly by rebounds driven by microbial and planktonic regeneration. On land, vegetation loss could take decades or centuries to reverse. But in the sea, foundational producers could return within years or even months. This difference in recovery speed fundamentally altered extinction dynamics, making marine ecosystems less prone to prolonged vacancy. Predators therefore evolved in an environment where opportunity returned rapidly after crisis, selecting for persistence rather than opportunism alone. Species that could endure temporary scarcity gained advantage over those dependent on stable abundance. This favored physiological flexibility, including variable metabolism and broad dietary tolerance. Over time, these traits became embedded in marine predator lineages, allowing them to weather disturbances that would have ended terrestrial dynasties. Parallel evolutionary pressures shaped land predators as well, but the oceans applied them earlier and more consistently. Teeth evolved to hold puncture and grip rather than slicing alone, reflecting the need to seize slippery, fast-moving prey. Vision and sensory systems expanded, because detection at distance often mattered more than confrontation at close range. Even reproductive strategies adapted to this environment, with live birth evolving in some marine reptiles to eliminate the vulnerability of returning to land. This shift severed dependence on shorelines, allowing predators to remain entirely within the marine system throughout their life cycles. As barriers dissolved, the ocean became less segmented and more globally connected, accelerating evolutionary feedback. Successful traits spread rapidly through populations connected by currents rather than constrained by terrain. Failure, likewise, spread quickly, as maladapted forms disappeared, without leaving isolated refuges, over millions of years. This pressure refined marine ecosystems into efficient machines for moving energy upward through trophic levels. Violence became not a destabilizing force, but a regulating one. The more dangerous the ocean grew, the more tightly integrated its systems became. Stability emerged not from safety, but from repetition. Each disruption tested the same pathways again and again, reinforcing those that recovered fastest. By the Middle Jurassic, the oceans no longer resembled experimental ecosystems, but mature systems hardened by constant stress. They were places where collapse was brief, recovery was expected, and dominance was maintained through endurance rather than conquest. In this way, the sea quietly solved problems of survival that the land would continue struggling with for tens of millions of years. As marine food webs hardened under constant pressure, the oceans began producing predators that mirrored land dinosaurs in function but not in form, because similar problems demanded similar solutions even in radically different environments. Speed became essential in both realms. Yet water transformed speed into an exercise in efficiency rather than brute force, rewarding streamlined bodies over muscular bulk. Where terrestrial predators relied on limbs to accelerate and turn, marine hunters converted their entire bodies into propulsion systems, minimizing drag and maximizing endurance. This distinction reshaped how power was expressed, because dominance in the sea favored sustained performance rather than explosive bursts. Ichthyosaurs evolved toward tuna-like profiles not by coincidence, but because hydrodynamics punished deviation with immediate energy loss. Plesiosaurs, despite their different silhouettes, faced the same constraints, forcing compromises between reach, maneuverability, and acceleration. On land, neck length often limited speed and balance, but in water, buoyancy allowed elongation without collapse. This enabled feeding strategies impossible on land, where long necks could probe schools of prey while the body remained distant and difficult to target. Parallel to this, jaws and teeth evolved toward gripping and holding rather than slicing alone, because prey capture mattered more than dismemberment in open water. Once seized, prey could be subdued through drowning or exhaustion rather than immediate trauma. These strategies converged with those of large land predators that relied on grip and bite force to control struggling animals. Sensory evolution followed the same pattern, as both marine and terrestrial predators expanded vision and spatial awareness to detect movement at distance. In the sea, however, light attenuation forced eyes to grow larger and more sensitive, increasing vulnerability to damage but improving detection in dim conditions. This trade-off reflected the relentless calculus of marine survival, where any advantage was worth the cost if it delayed death. Hearing and pressure detection also expanded, allowing predators to sense vibrations and movement beyond visual range. These adaptations created hunters that perceived the ocean not as empty space, but as a constantly shifting map of signals. On land, scent often filled this role, but in water, chemical trails dispersed quickly, elevating the importance of motion detection. As a result, marine predators became specialists in interpreting fleeting information rather than persistent cues. This specialization reduced reaction time but increased dependence on constant attention. Mistakes that could be corrected on land often proved fatal at sea, because recovery required energy that might not be available. Over time, This pressure favored cognitive efficiency, selecting for behaviors that minimized wasted movement. Hunting strategies became less theatrical and more procedural, relying on positioning, timing, and anticipation. This convergence with land predators was therefore functional rather than visual, driven by shared ecological mathematics rather than shared ancestry. Both systems selected for animals that could dominate energy flow rather than territory. Yet the ocean amplified these pressures, because prey densities fluctuated rapidly, forcing predators to adapt continuously. Land ecosystems changed slowly by comparison, allowing successful strategies to persist longer without modification. This difference accelerated marine evolution, compressing adaptive cycles into shorter spans. Traits that worked briefly could spread widely before being replaced, creating lineages defined by flexibility rather than stability. As predators grew larger, their prey grew faster, reinforcing a feedback loop that favored extreme performance. In this sense, the Jurassic oceans became laboratories of convergence, where land-like solutions were tested under harsher constraints. When similar forms later appeared on land, they often echoed marine precedents rather than inventing entirely new strategies. The sea therefore functioned as an evolutionary proving ground, refining designs before they appeared elsewhere. This relationship was not directional, but parallel, with each realm solving the same problems independently. Where one succeeded, the other eventually followed. The danger of the oceans lay not only in their predators, but in the pace at which adaptation occurred. Survival required constant adjustment, leaving little room for specialization that could not bend under pressure. In such an environment, dominance was temporary by default. Even apex predators existed on borrowed time, measured in millions rather than tens of millions of years. The Jurassic seas therefore produced not timeless rulers, but relentless successors. And through this cycle, the oceans quietly demonstrated that danger itself could be a stabilizing force when change never stopped. When disruption struck the Jurassic world, the oceans absorbed shock differently than the land. Because water distributed damage across space instead of concentrating it in place. Volcanic eruptions, climate oscillations, and sea level shifts altered chemistry and temperature rapidly, yet currents prevented any single region from remaining isolated long enough to collapse entirely. Heat and nutrients moved laterally through basins, redistributing stress rather than allowing it to accumulate locally. This constant motion transformed catastrophe into gradient rather than boundary, blunting extremes while extending influence. On land, disruption often severed continuity, isolating populations behind damaged soils, altered rivers, or destroyed vegetation. Recovery on land therefore required reconstruction from fragments, a slow process dependent on stable conditions that rarely returned quickly. In contrast, the oceans rebuilt from below, because microbial life and plankton responded almost immediately to changes in light and chemistry. Even after severe perturbations, photosynthetic organisms reoccupied surface waters rapidly, restoring the base of the food web. Once energy returned at the bottom, the rest of the system followed with mechanical inevitability. Zooplankton bloomed, small predators followed, and larger hunters tracked abundance through movement rather than waiting for regrowth. This sequence unfolded repeatedly across the Jurassic, turning recovery into routine rather than exception. As a result, extinction in the sea often meant turnover rather than vacancy. Species disappeared, but roles persisted, filled by lineages already adapted to instability. This continuity allowed marine predators to maintain pressure even as specific actors changed. Ichthyosaurs and Plesiosaurs endured not because they were immune to disruption, but because their environment rewarded persistence over optimization. Their survival depended on the ability to relocate, endure scarcity briefly, and exploit rebound faster than competitors. Land predators faced similar pressures, but slower recovery amplified losses, making extinction more final. Forests collapse, removed shelter and prey simultaneously, compounding vulnerability. In the ocean, shelter was movement, and prey was distributed rather than fixed. This difference reshaped evolutionary expectations, favoring marine lineages that treated instability as baseline rather than anomaly. Over time, this produced oceans that were not fragile despite constant stress, but robust because of it. The system learned to expect interruption and respond automatically. Oxygen dynamics further reinforced this resilience, as well-mixed waters prevented prolonged anoxia across large areas. Even when oxygen dropped locally, Circulation reintroduced it before collapse could cascade. This buffering allowed high-energy predators to persist without exhausting their environment. The cost of failure remained high, but failure rarely propagated far. Each disruption therefore sharpened the system instead of dismantling it. Marine ecosystems evolved toward redundancy, ensuring that no single loss halted energy flow. On land, redundancy was limited by geography and slow reproduction. In the sea, redundancy emerged through connectivity and speed. This contrast became most visible during periods of global stress, when terrestrial ecosystems lagged behind oceans by millions of years in recovery. The Jurassic seas often returned to functional complexity while continents remained simplified and sparse. Predators exploited this asymmetry, maintaining dominance offshore even as land systems reset. The ocean thus became a refuge for continuity during times of planetary change. Danger persisted, but collapse did not linger. Survival favored those who could endure brief absence rather than those who required constant stability. Over geological time, this pattern rewarded marine systems with evolutionary momentum. The oceans did not resist disruption by avoiding it, but by metabolizing it. In doing so, they transformed catastrophe into process. And by the late Jurassic, this capacity made the sea not just dangerous, but dependable in its relentlessness. By the late Jurassic, the oceans had completed a transformation that made them fundamentally different from the land, because survival there no longer depended on isolated dominance, but on uninterrupted performance across constant pressure. Marine ecosystems had learned how to absorb loss without pausing, replacing vanished species with functional equivalents faster than memory could form. This continuity meant that extinction rarely produced silence, only turnover, as roles persisted even while names disappeared. Ichthyosaurs and Plesiosaurs existed within this system not as tyrants, but as participants locked into a cycle that rewarded endurance more than supremacy. Their success was measured not by how completely they eliminated rivals, but by how consistently they remained effective as conditions shifted around them. Over millions of years, this produced oceans where danger was no longer episodic, but ambient. Predation did not spike and retreat, but remained constant, pressing every lineage equally. In such an environment, evolutionary experimentation accelerated, because failure was identified quickly and erased without delay. Traits that offered even slight advantages spread rapidly through connected populations, while ineffective strategies vanished without leaving refuges behind. The ocean, therefore, became a place where adaptation mattered more than inheritance. Lineages survived not because they were well established, but because they could remain functional under changing temperature, chemistry, and prey availability. This selected for flexibility rather than specialization, embedding resilience directly into marine biology. On land, ecosystems relied on stability to maintain complexity, but the sea maintained complexity by assuming instability. Forests required time to regrow, soils required centuries to recover, and terrestrial food chains often stalled while waiting for foundations to return. The oceans bypassed this delay by rebuilding from microscopic life upward, allowing predators to re-enter systems long before landscapes healed. This asymmetry reshaped the balance between realms, making the sea a place of continuity while continents periodically reset. Marine predators therefore experienced a world where competition never paused, forcing constant refinement rather than episodic dominance. Size increased not as an expression of control, but as a buffer against unpredictability. Speed evolved not for pursuit alone, but to ensure survival across fluctuating prey distributions. Sensory systems expanded because detection, not confrontation, often determined life or death. Over time, these pressures produced animals that resembled processes more than personalities. They were not singular rulers, but repeating outcomes shaped by identical constraints applied again and again. The ocean did not remember individual predators, because its logic did not require memory. It rewarded motion, punished hesitation, and erased inefficiency without ceremony. Even apex hunters existed under the same scrutiny as their prey, because injury, aging, or misjudgment carried immediate consequences. There was no safe plateau where dominance could rest. This made the ocean an environment where danger itself became stabilizing, preventing stagnation and limiting unchecked expansion. Violence did not destabilize the system, but regulated it. Each successful predator applied pressure that shaped prey, which in turn shaped the next generation of predators. Through this feedback, balance emerged not from peace, but from constant recalibration. The Jurassic oceans therefore represent one of the earliest examples of ecosystems optimized for continuous stress. They did not resist disruption by avoiding it, but by metabolizing it into structure. Long before land ecosystems achieved similar resilience, the sea had already learned how to survive without pause. This history challenges the familiar image of dinosaurs as unquestioned rulers of their world. While they dominated continents, the oceans had already moved beyond dominance, toward the most dangerous environments on Earth were not those that destroyed life outright, but those that forced it to adapt without rest. In the Jurassic seas, survival meant never fully recovering, only continuing. And in that unbroken continuity, the ocean became not just a setting for evolution, but its engine. Long after individual species vanished, the logic of the sea remained intact, carried forward into later ages. And if you choose to stay with these stories of deep time and quiet persistence, you're always welcome to follow along as we keep exploring the worlds that shaped life, long before it learned how to remember itself.